Hi guys, I don't know if you can hear me. Let me know if you can, and let me know if the audio levels are okay today. I know there were some issues in the last presentation, so just let me know. Maybe I can tweak it here. Are we getting a better audio this time? Are you hearing me? Let me know if you're hearing me. Okay, clear sound. Thank you, Glass Chappy. Okay, so literally look back through a school revision book for physics today and saw a picture of decay chains and the dating of the Earth using uranium and lead and intermediate isotopes in rock. Yes, Ron. Uranium has a 0.3 of the supposed life of the universe, and so it gives you a kind of good idea of how far we are along. But there's plenty of uranium actually, assuming no lead is present when rock is formed. Yes, there is that. And it would appear that using high intensity relativistic discharges, lead is a preferred thing to be synthesized actually. And using extreme cavitation or relativistic discharge, as in the first case Leclerc and the second case S.V. Adamenko, they were able to create uranium and actually elements that don't exist in the near universe in the case of S.V. Adamenko. So it kind of causes a problem for us in determining what the age of the universe is, because if it was an extremely intense discharge or electrical event akin to an S.V. Adamenko discharge, but on a much more massive scale, that created Earth, let's say, then the age of the universe is only from our perspective. Of course, then someone might look out into the cosmos and see the spectral lines for elements out there and debate on that basis. Looking forward to presentation. Thank you, Ron. Okay. Hey, CNC machine, fantastic. Good evening, Jason. Okay, just let a few more people come into the room. Is it rather faint? It's a bit quiet, is it? Right, let me see if I can fix that. Is it better now? Is it better now? I don't want it to clip. Is that better? Hi, Hank. Ron, Mark, Junie. Hi, Artifact. Hi, David. Okay, so what am I showing you at the moment? It would be useful to know. I'm going to show you something different. Hopefully you'll see this in a second. Now, is that coming through? Yes. Okay, I can see how it's going now. Actually, Mark, this isn't... yes, it is. It is, but it isn't. What I'm talking about today is an extension of what I was talking about in a recent test article on remoteview.icu. And by that I mean some ideas that I've been having in my head for a while and I hadn't quite fully formed, I would put into the private part of remoteview.icu, and to put it out there as a kind of like a flag in the sand, as it were. And I put out a presentation recently, and I will go and look at that in a little while. Let me just look at the name. For those that subscribe to my remoteview.icu newsletter, it's the article called Untimely Decay of Fully Ionized Atoms. And I will come and show you, I'll actually walk through that blog here in this presentation to a degree before I get on to what I call the money shot. But for now, I'm going to refer to this paper by Ken Shoulders, and it was from 2005, and it's called, and you can get this online, and in fact I will give all the links at the end of this, but this is from Rex Research, so you can go and look at Shoulders' papers on Rex Research, and perhaps I can I do that? No, it won't let me do that. Yeah, it's Rex Research, and it's a directory called Shoulders, and if you go / after that, you should see all these files, and this particular one is called Electromagnetic Pulse Source Using Fluidized Electrons Appendix. And the reason I wanted to talk about this is, first off, is because I tried to find this paper when I was doing the last presentation, and I was trying to find this particular image here, which you can see. And what Ken had done is he had put a chromium film on glass, and this is the cathode, and lower down, I'm actually showing you that I'm showing you the wrong window at the moment. This is not helpful. I'm very sorry, but you're just looking at the title frame. So let me switch to Adobe Acrobat. And I will switch over here. Right, so maybe I've got control of it now. Okay, good, I've got control of it. You can see what I'm trying to show you now. So this is called Electromagnetic Pulse Source Using Fluidized Electrons. And there's a number of strike marks and so on. And so you can see these kind of strike marks that we saw in the Vega Valley sample, in the principally in the what I call the Eastern Plateau. And these are going across the surface, in this case, of whatever material he's looking at here, the substrate. And there's a paired EVO. But what I'm referring to, or tried to show you in the previous presentation, was this image here. And this is a chrome film on glass substrate. And this is the cathode. And what Ken is saying is, if you look at this, you can see this balling up. Now we got this balling up with some sort of film deposit, that was on our Vega Valley Henck's brass cathode. And you can see the balling up, but the balling up's a little bit more interesting on Henck's cathode. But what Ken is saying here is that these are actually tributaries feeding this central point here, where the EVO was actually launched from. And so effectively, the EVO is coming from this point where the three sort of sets of tributaries meet, and it launches out of there. And in the process of the electrons flowing towards there, it's kind of melting the chrome film. The other one here is the anode, and that's the strike mark of the anode. And he's saying that it actually came in from the left side, and it left a shadow. It actually changed the chromium material here as it was coming in from the left before it struck the film and cut through it. And so he says quite clearly here, this data further reinforces the notion that EVOs do not necessarily stop completely upon first contact with the anode. There may be motional aspects to them leading to diverse radiation patterns. It says the dark streak on the left is actual and is apparently caused by the approaching EVO modifying the chromium as it skims the surface looking for a landing spot. An EVO is an exotic vacuum object. It was originally, thank you very much, Mark, it was originally something that Ken Shoulders called electron validum, which is like strong electron, because he knew at least that they were made of electrons. And kind of is an exotic matter type in that it's not what we're normally made of, although we may actually have some of them in us and in our water, in our body and so forth, but that's another topic. But not at the quanta that does us lots of harm, obviously. The exotic vacuum object is the third name that Ken Shoulders gave to it. So it's EV originally, and he wrote a book called EV, A Tale of Discovery. And if you go and search for that on Martin Fleischmann Memorial Project's page, you will actually see you look for EV A Tale of Discovery, you'll be able to find the link to that book, and so you can go and read that. It was formerly secret, and then he then called it high density charge clusters, because he realized that there was positive ions in there as well as the electrons, and that they were all traveling together. And then he realized there's more to it than just ion electron grouping, and so he moved away from the high density charge clusters to exotic vacuum objects. Now, Takaaki Matsumoto, who came in 1989, he immediately started calling these things itonic clusters, and he says that there are ions that can be trapped inside it. However, other than ring and spheres, they can also form these itonic mesh balls, and that the mesh is made of positrons, electrons, and neutrinos, and so it's really quite an exotic structure that this made from, and that basically you can make matter, transmute matter, and destroy matter with this technology. So it's the full tool set, as it were. Anyway, back to the paper in hand, and in fact, I'm probably going to switch to the web view because it's just faster. I'm going to go here. So this is the same paper, but just in this is in a web browser. So you've got a couple of strike marks here, and these are other strike marks. You can go and look at this in your own time, but there's an associated document. So this is actually the appendix. This is the document, and it's electromagnetic pulse source using fluidized electrons. A new electromagnetic pulse, EMP technology, is proposed based on the rapid decomposition in lightning-like fashion of a cubic centimeter quantities of fluidized electrons, yielding both high-energy particles and high-intensity electromagnetic fields capable of deep penetration, massive disruption of electronic systems, and having a long-range, low lethality electric stun gun effect of high accuracy. A simple deployment method is proposed using ballistics by incorporating fluidized electrons into rounds of ammunition ranging from .22 caliber to 20 millimeters. The possibility of more sophisticated guidance means by employing a beam of light is also introduced. So what he's saying is that these exotic vacuum objects can pack a real punch. And if you read through this, now, in his book, EV A Tale of Discovery, in the conclusion, he does say, and actually, to be honest, I have not read the book. I read the conclusion on Rex Research. I kind of like to clean room my research, so I like to try and come to conclusions and then be delighted when people made the same conclusions many years before me, looking at similar evidence. And anyway, the point is that it's important to introduce what Shoulders very well understood, because it relates to the proof of Lena, which I believe has already happened. We just didn't realize it at the time. Well, we did think we'd proved Lena, and I still stand by that. But I think there's more to be found. Now, in his conclusion of his book, he says that the EVO can act as a monopole oscillator, and that it produces scalar waves, and therefore, if it's also producing them, one might imagine that it could accept scalar waves. So it's a transducer in that respect, and so a deep penetrating EMP technology might be something that uses scalar waves. So a Faraday cage would not protect you. And this is something that it seems to be what is observed when you are working with Lena, and sometimes these things can blow up. However, if you looked at the Occam's razor presentation that was given last night, we put it on our channel last night, Andras Kovacs was saying that the neutrino, as far as they can work out, may actually be a scalar wave in terms of the way it travels. So it's kind of a bit like light, but rather than being an EM wave, it's a scalar wave. And so this kind of does fit into potentially what's going on. Anyway, if you read down through this paper, it's actually quite shocking. It says the ion recombination flash of visible radiation seen from decomposition of a 10 micrometer diameter structure is shown in figure 11 and figure 12 of Appendix 1 and discussed in the accompanying annotation. The flash has a volume of about 1 cubic centimeter. 1 cubic centimeter. Now, I believe this is what we saw in the Evo blaster. So if you go to our YouTube channel and you look for Vega Evo blaster, I would suggest that these were EVOs that were in dark mode that were re-excited upon contact with the cathode, and they were around about the 10 micrometer diameter, producing a 1 centimeter explosion. And so that's that one. Shoulders goes on here in this paragraph to say a naive calculation of visible flash volume using linear assumptions from an initial 1 millimeter cube of such material is 1 cubic meter, and from just 1 centimeter cube of condensed electron, what HEP-EMP is just his name for this type of EMP. It's a source from that one centimeter cube of this fluidized electrons. When that blows up, it produces an EMP flash volume. So this was, you don't want to be anywhere near this, 1,000 cubic meters from a 1 cc of this material. A volume much larger than this is more likely from a sequential EVO disintegration extended over space and time. Now, he says this is equivalent to the flash that you get from a nuclear bomb, and the initial flash, and which actually, as far as I understand it, contains neutrinos, and this is what creates the EMP from a nuclear bomb. So this is like the EMP you get from a nuclear bomb, but without the nuclear bomb. It's this detonation of fluidized electrons. It says, as shown in figure 13, an EVO having a diameter of 20 micrometers bores cleanly through a thickness of solid material having an average atomic mass of about 30 to a depth of ½ millimeter. The slug of recovered ejected material having dimensions of 20 micrometers by 100 micrometers is projected to a velocity averaging 10 to the 7 centimeters per second. 10 to the 7 centimeters per second. Now I'm going to go somewhere and share with you something that I shared, I think, in 2017. It was in June, and it was a day or two after it happened. So I'm just going to find it right now, and then I will be with you in a second. I think it was in June. So this is an Arabic journalist called Jenan Musa, and she was on the ground in Syria, and she's giving her account on July the 7th, 2017, and she says, Syrian Defense Force fighters in Raqqa said US uses electricity bomb against ISIS. They call it electricity bomb here because they don't know the real name. When a plane wants to drop electricity bomb, we are told to drop anything metal that we carry. Otherwise, we also burn like ISIS fighters. Also, met on the front west in Raqqa, Syrian defense fighter who has found an ISIS house, a huge sword. ISIS used to cut limbs and something with it. I don't want to say these things, but it's there. And essentially the sword, if you look in the image, is very, very corroded. And this is something that you would expect from something that's been exposed to exotic vacuum objects. Anyway, so there's more in this tweet. There's a couple of sections missing, but maybe it's there. But you can go and look up Jenna Musa from July the 7th, 2017, and talking about these kinds of technology being used in the battlefield. So Shoulders is telling you specifically that this can be made, that it has this kind of output. And we experienced something like this, if you recall, in what I called the cookbook is in the signal. In fact, in brief, is signal. And this is a step-by-step that we did, and so I will cut there now. Sorry, did you see the Jenna Musa thing? Did you see what I was showing there in the it's this. Hopefully you saw that. Anyway, this is something that was released on the 22nd of February 2016, and in here we just detailed the process that we chose for an experiment called Glowstick 5.2. And in Glowstick 5.2, we had an event which was picked up by a member of the crowd called Echo. It was in the middle of the night. And it was a couple of traces that had extremely high changes in count in the scintillator. Absolutely huge. And so you can see here it's showing the normal sort of events and average around the long-term average. So there's nothing really. But when you get to 7 and trace 8, there is this big spike, and even on trace 10 a little bit. And this was the experiment. And the part in question was interesting in that it was the first time we went through 1,000 degrees centigrade. So the part of this experiment where this occurred is the first time this experiment went through 1,000 degrees centigrade. And this is interesting because Parkhomov's hadn't published his theory at this time. Actually, Parkhomov's 225-day reactor is based largely on this this actual process of going through the experiment. And so there's this radiation signal, but more importantly, there was 2 events that occurred at the same time. There was the spectrometer basically was saturated, and it says here that a large percentage of, or the largest percentage of lost pulses was in this Spectrum 7 event. And in addition, our power monitor went out for a period of time. Okay, so these are the composite of these together, and so you can see trace 7 is this red line, and you can see its elevated counts across the entire line. And what's very interesting about this is there are no characteristic X-rays. There are no characteristic X-rays. So if you would imagine what we are doing in this particular experiment is we were attempting to, as best as possible, replicate, do a mashup between Parkhomov, Piantelli, what we'd learnt from Piantelli, and the Rossi patent formula. This is lithium aluminium hydride and nickel powder in there. So it was a 3-way mashup. And this was a striking signal that was achieved here. And as I say, the important thing here is there's no characteristic X-ray. And why is that important? Well, at the time, Mathieu Vallat asked one of his associates, who was an expert from the French Nuclear Authority, what's going on, and there was he said that this looks like it's a huge Bremsstrahlung radiation release. So you had a very large amount of beta particles going through some material and producing this large spectrum of signal here. Now the interesting thing is that, as I say again, there is no characteristic X-rays. You know, Thomas Barkla won the Nobel Prize in the 1910s, I believe it was, for discovering characteristic X-rays. And what this is if you have a high energy, say beta particle, and it's going through or an X-ray basically, or a beta particle going through a heavy element, for instance, or an element, it would produce a characteristic X-ray, and this is what you use in EDX to determine the elements that you have in your material when you are trying to analyze it to see what elements it has. And so if this came from inside the reactor, then we have Cantal wire around the outside, and the scintillator is in an aluminium sort of casing, and it's set into a lead cave. And in fact, if I bring up the imagery here of this, I've got it here. Sorry, this is a lot of up and downing for you at the moment. So this is actually a paper that was written with Bob Higgins, called the iceberg in the glow stick data. Is that all it is? Have we got more to it? So you can see here that on the left hand side you have the head of the scintillator, and there's a distance between that and the active, so-called active side, and you can see that under this alumina sheath you have the Cantal heater wire here, and over here, interestingly, there was one of these relatively affordable metal sheathed what do you call it, Geiger counter, and that didn't register anything. Absolutely did not register anything, and that is very important. We'll come on to why that is very important later. Now, in the picture on the right here, you can see the lead brick on the top here. So there was actually a lead brick on the top, but that's been removed on the picture on the left. So if we had extremely high energy beta particles coming out of here, you can imagine that there would be some characteristic X-rays from the interaction with that, with the lead and so forth. Okay, and so why are we not seeing any characteristic X-rays in here? And in fact, the background counts, this is from Bob Higgins's work, this is the total background counts and so on. There's a ratio of 5.44, so it's very much higher than the background, and this very smooth curve. Now, we had seen something kind of like this before. Now let me go back to this, and when I was discussing this at the time, there was a number of things around the time. So I don't know whether Rossi had used lithium aluminium hydride from the get-go. I don't know, but it was claimed that he had gamma radiation, you see here, between 50 and 100 kiloelectron volts with no outstanding peaks. And he had a relationship with a group called Defcalion Green Technology, and they claimed gamma radiation of 300 keV and below. Okay. Now, if you look at our data, the spike, which is only momentary, actually goes well above 300. But this trace 8, that's the subsequent sampling range, is actually only below 100. In fact, it's below sort of 70 or something like that. And there's a cut-off here on the window of the scintillator. The actual, it can't detect things in this range. It hasn't got that low energy detection below 30. In fact, it's actually around about 50. There's a drop-off. So this would actually be even more accentuated because there is this drop-off. Okay. So, and for years we thought this was a fairly unique finding. Well, actually not for very long, because almost immediately we realised that Rossi claimed something and Defcali and Green Technologies had claimed something, and then subsequent to that we had quite a few other people claiming something similar. And so there's a couple of things. So we've talked about EMPs from fluidized electrons on shoulders. So let's call that done. We've also experienced in 2013 what we called gamma at the time, and this was when we were recharging a Celani cell. It had a leak in it, and it was going down from 3 bar down to 1 bar, and we were refreshing it with hydrogen, and we would get this sudden burst of radiation coming out, and it would. And I stopped whatever I was doing, and I flew to France, and because I wanted to see it with my own eyes and record it and make sure it was on. So we actually captured it on camera, and so forth. And we looked to get a scintillator, but for whatever reason, that didn't work out as we hoped. But anyway, the point being is that every time we recharge this, it produced this radiation signal, like 2.5 or 3 times the emissions from background, and then it decayed away rather rapidly. And in years after that, I hypothesized that what was going on was there's some sort of stable state that had built up on the wire. And when you put the fresh hydrogen in, it gives a shock to it. It breaks up that stable state. I didn't know what that was at the time. And then it takes time to settle down. And as it's settling down, it's kind of like, it's in a very dynamic state. And it's throwing out this radiation. And so that's where I was at that time. And this is interesting because of 2 different things. One is Thermocore. This was actually Mills in the early 1990s. He was working at an organization called Thermocore, and they had nickel powder also, like we had in our glow stick 5.2, where we saw that spike. And they were doing hydrogen, just protium, and they had what they called their singularity. And they don't know what temperature it reached, but when they put the fresh hydrogen in, the DWAR, which had about 1 pound or something of this prepared nickel, the steel on the DWAR glowed yellow-orange as if it was very hot. And this is interesting because you see this in the sapphire experiments before they put some shielding inside and then put it in water. And why I'm saying that is interesting is because I don't necessarily think that's heat in the traditional sense. I think there is a coherent matter that's formed in the process of putting that in. Now, the reason I say that is that you can go and look at studies done by that I have reported on the MFMP channel, where Parkhomov and Bazhatov were looking at radiation coming from metals, and they found, I think, over 200 degrees and below 350 degrees with a range of hydrogen absorbing metals. You got this weird kind of radiation out that they weren't fully aware of what it could be at that time. And then I think in 2012 going into 12, Edmund Storms and Scanlan at Kiva Labs, and I've done another presentation on this, they observed some form of radiation that was able to go through glass, through aluminium, through, I think, stainless steel, and it was then that something happened in the detector. And I argued, and he didn't know what it was, but I argued that it was potassium-40, and fluorine, which are in the mica window, which interacted to enable the signal that they saw, which is a specific decay rate, which, to be honest, I would have expected him to know, but it wasn't discussed in the paper. So I hope that I solved that. But again, this was a case of having, I think in their case, it was between 250 and 300 degrees. Now, in our case, we were told by Piantelli it's between 100 and something around about, we calculated it around about 179 and up to 350 degrees. And these are important temperatures. But in every case, it was having the material prepared, degassed, vacuumed out, and at temperature, and then you put the hydrogen in. In the case of Celani cell, that was actually replicated by Jean-Paul Biberian, the one that I've got on the screen here. That was replicated within 24 hours. Now, at the time that I wrote this article, so before I read through what I've got here, I want to talk about also Zatelepin and Baranov. They found that, this was actually in 2017, they found that if they had a large amount of prepared PNK02 nickel, this carbonyl nickel that Parkhomov used, if they prepared that in a kind of typical Parkhomov way, the same way I described in the cookbook as in the Signal, or Signal for short, if they then put in hydrogen, the entire lab, according to their observation with what they had been able to work out, they could detect it with, their entire lab was being filled with strange radiation. And it was at that point that Zatelepin and Baranov decided to not work with nickel hydrogen type systems and similar systems until they better understood strange radiation, because Bajatov had died and they blamed it on strange radiation. And this reminds me also of the David Hudson, where he took some monatomic gold, like this white powder in here, and he had a thumb-sized tungsten electrode in a electric arc furnace, and he went and touched it, and the tungsten disappeared. But more importantly, twice he did this with the tungsten electrode disappearing, and it was supposedly good for thousands of melting, but it didn't last one. He had glass, like borosilicate glass, on the walls around his laboratory, like jars that crumbled. Okay, so there was a flux of radiation coming out, and Leclerc also observed this in cavitation, where he would observe these spiraling tracks in a long way away. I think it's even in a tree outside or something, a very long way away from where they were doing the experiments. So there is a history of this flux of radiation coming out. So it's not just that you get the EMP, it's that you actually have some material that's coming out. And in the case of Shishkin, if you go and look at a new form of penetrating radiation or something that I have on the MFMP site, something along those lines, Alexander Shishkin worked with a team since 2009 to 2018 when he gave his presentation in Sochi. And they concluded that the neutral form of the exotic vacuum object, which exotic vacuum objects they term with something that makes a little bit more sense. They call it magnetotoroelectrical radiation. The neutral form of that he calls a string vortex soliton, and he concludes that because of what it does and the way it can travel through things and the way it interacts with radioactive isotopes, they concluded that it could be a condensed cluster of cold neutrinos. Okay, so that's where they are with that. And so that brings me on to talk about what I was suggesting the other day. But so I'm just going to leave this up, and I'm going to switch to this presentation that I gave on my blog called Untimely Decay of Fully Ionized Atoms. And I gave this presentation, sorry, it wasn't a presentation, I gave this on the sort of closed area of my blog just to get it out there whilst I was still thinking about it. And it's called Untimely Decay of Fully Ionized Atoms. Can playing with stability lead us to a strange radiation flux detector? And essentially, what it is during that Sochi Cold Nuclear Transmutation and Ball Lightning Conference in Russia in 2018, Leonid Oretskov, the guy that gave strange radiation its name, strange radiation, shared this particular slide, and you can go and see the whole presentation, and the slides are available in English on our MFMP YouTube channel. And you can see that he quoted that some nuclei, like 163 dysprosium, 193 iridium, and 205 thallium, are absolutely stable in the neutral atom, but they become beta active at complete ionization of the atom. And interestingly, this first paper is 1992 and the second paper is 1985. And I go on to talk about this one, which is my key isotopic transition here, which is 205 thallium to 205 lead. And this again, I will say, is from 1985, okay, by a guy called Henning et al. And what they found is 205 thallium, which is one of the two isotopes in thallium. Let's just check that. So we have two isotopes in thallium. There's a there's a synthetic one, but it's basically 70.5. If I go here, 70.5% of thallium is 205, and it's stable. It's stable to the end of time. Absolutely, it will be there and it will be stable till the end of time. And so what they found was, if they fully ionized it, that it then decayed to lead 205 with a half-life of 120 days. Okay, so it goes from basically a half-life of infinity to a half-life of 120 days. And so the interesting thing about this is that the product of that, which is lead 205, it has a half-life of 1.73 times 10 to the 7 years by one account, and approximately 15 million years. So it's about 17 million years. And it does this by electron capture. So if you've got a situation where you've got something that wants the electrons more than the lead 205 does, then it's never going to decay back in our EVO. And the interesting thing is that since even before 2015, they have considered thallium 205 as a potential solar neutrino detector. So this is in the state in 1987. You've got all these elements. So if you fully ionize tritium, it will decay a little bit faster, 1.01 times the normal rate of decay. If you fully ionize carbon-14, it will decay slightly faster, 1.01 times. But if you come down to dysprosium, or you come down to iridium 193, or dysprosium 163, or you come to thallium 205 or plutonium 241, you can get an infinite increase in the rate of decay because the denominator is 0. Okay, but thallium is totally amazingly interesting because it decays to this lead isotope, which does not exist naturally in nature. So if you wanted to prove 100% that you had something that had been caused because of some transmutation process in your reactor, what better is something that's stable for 15 to 17 million years and comes from an isotope, and the only way it can get there is from not only full ionization, it has to have had an incident neutrino. It has to have had an incident neutrino. Okay? So we're in a situation here where I put forward that this might be a way to detect if Alexander Parkhomov is right. If you go back all the way to the Russians in the 1950s, the first people doing palladium deuterium boiling water reactors I can't remember his name just now, but I will at some point. But anyway, he found that there was this emission of some form of radiation that was affecting half-lives of materials, and many people have reported these things. And so if it is, as Shishkin and his team at Dubna are suggesting, it's a cold neutrino condensate is coming out, or it is, as Parkhomov is saying, they are technologically synthesized cold neutrinos, or it is, as it is being said by Takaaki Matsumoto, that in the mesh, this itonic cluster that is on these micro ball lightning, they contain neutrinos. He doesn't say they're cold neutrinos. It wasn't a discussion point in his work, but he's saying that they contain neutrinos. You have a number of different independent people that are saying this is neutrinos. If it is, or it has them in there, if it is, then we potentially have a way to prove this. Now, I have talked about in this presentation how we saw this particular signal here. And what was unique about it is this curve. Now, you know what? You often aren't the first people to find these things. And here's a presentation that was shared by Can. And it's, let's go to the top here. It's in the Journal of New Energy from 1996. And if we go down and try and find it, somewhere here. It's a paper by Matsumoto, and if I can find it, maybe I can do a search. Oh no, isn't it? Is it going to do it for me? Maybe it'll do it for me. Oh, maybe it's done it for me. Okay, no, it's not done it for me. Give me a second, I will find this. Now, Fox, who's the editor of this paper, actually bought the Shoulders patents as far as I'm aware. So a lot of this particular presentation is talking about something similar. And in fact, Takaaki Matsumoto conceded that he probably had rediscovered Ken Shoulders' discovery. Oh dear. Okay, so here we go. Matsumoto, Takaaki Matsumoto. So, experiments of sparking discharges were performed in ordinary water. And so he has this scintillator up here, and he's got his discharge here between these two things. And he used nickel, palladium, titanium, iron, cadmium, molybdenum, tungsten. And he had potassium carbonate in there. But the interesting thing I will draw your attention to here in this presentation was this discussion on emission of radiation. He says the emission of radiations was monitored by the cesium iodide scintillation spectroscopy. Certain kinds of radiation were observed to be released through the wall of the glass beaker. The cesium iodide scintillation detector was alternatively placed outside the glass beaker and over the water surface. The detector measured the emission of radiation in the high voltages in both cases. The energy spectrum of the radiations were continuous and monotonously declined as the energy decreased. This is essentially what we observed. This monotonous decline. There is no characteristic X-rays in here. Okay? It says the counting rate was significantly higher than the background. As the voltage increased, the energy tail expanded more widely. The intensity of the radiation sharply dropped as the distance between the detector and cathode increased. The radiation detection was neither gamma rays nor X-rays. He's specifically saying these are not gamma rays or not X-rays. The signals were generated by electromagnetic waves picked up with the electrical circuit The emission of the electromagnetic waves will be discussed relating to the breakup of, he calls it ironic clusters, it's a spelling mistake, but itonic clusters. So he's saying what he says is probably the same thing as an EVO has blown up and it's caused this EMP. Exactly what Shoulders is saying, exactly what we thought could be the reason for what happened in our test. Now, there's actually something down here I want to draw your attention to also, maybe. These are some hexagons. These are some various different things here. One last thing. It's actually relating to talking about nuclear transmutations. Oh, there's something in here I want to capture for you, and maybe I can just find it because I have some notes. So maybe I can go to my notes here, and you can't see those. But he basically says on page 89, he says, here the breakup of the ring clusters could make the electromagnetic waves, as were detected by the scintillator, similar radiation could also be emitted by the breakup of itonic hydrogen clusters. Okay. And so he's saying this. Now, why is this important? Why is this important? Well, I'm going to read you here an account. And this is from January the 14th, 2011. Rossi and Ficcardi gave the first public demonstration of low temperature ECAT to a personally invited group. A short time afterwards, Francesco Celani, who was present at the demonstration, sent a review for the event to New Energy Times. So there's an account in here you can go and read on our website. In this article, it is noted that Rossi and Ficcardi had a twin gamma ray detector set up in order to detect positron and electron annihilation that was expected by Ficcardi based on previous experiments. The results from that setup were not meaningful during the guests' time in the room. Bob Grenier, this is me, was keen to understand more about this event, so in the day following ICCF 18, that was in University of Missouri, he quizzed Francesco on the matter. Here is a fresh account of that event. Francesco was sitting down with other scientists and guests waiting to be called in for the demonstration. They were 7 to 8 meters away from the ECAT, which was behind a door in another room. Francesco had 2 gamma detectors with him. One very cheap and one very expensive battery-operated sodium iodide detection range of 25 keV to 2000 keV. This is the range that you see in the paper by the 1996 paper by Matsumoto, and this is the range that you see in our GS 5.2 data. He notes that the background in Frascati is normally around 120 because of local geology, but in Bologna it is 60. Francesco Celani set the detectors accordingly, and the assembled group sat there patiently waiting. Suddenly, and for about 1 second, both detectors topped out at 1,000 plus counts per second and sounded their alarms. They could not show any more. Several of the invited observers considered literally running from the building, as it was speculated that Rossi might be leveraging a radioactive source in his experiment. Why such concern? Well, radiation falls off according to Newton's 1/d squared law, as you can see here. Plugging the minimum 1,000 counts per second and 8 meters into the formula would mean that 50 centimeters from the ECAT, the counts would be over 250,000 per second. Not good. However, luckily, the momentary signal collapsed, and about 2 minutes later, Rossi came into the waiting room to invite people in to see the ECAT, saying the reaction has started. Francesco and the rest of the invited guests went into the room where the ECAT was. Whilst in that room and using the sodium iodide detector near the operating reactor, there was a 50 to 100% count increase over background, which was erratic. Francesco decided to try and get a spectrum from the detector. So up to this point, he'd only been using it in the mode of looking at the overall count rate. He hadn't looked to see what the spectrum was, this 25 to 2000 kV. In order to understand what might be going on, and so he switched mode on the detector. Rossi, however, saw what he was doing, got upset, and Celani was told to stop the measurements, which he did. So, why am I telling you all this? Why am I telling you all this? Why is this interesting to you? Any guesses? What have I left out? Has anyone guessed what I'm about to say? I'll give you a few moments to think. Has anyone guessed what I'm about to say? Anyone got an idea? Oh, that was the thing that I was trying to show Gardy Pierre. In that presentation, that paper from in here, Matsumoto, he actually refers to the fact that almost nothing this guy didn't see. Here, look at this. This is in the same paper. The second is a special kind of product represented by tiny white holes. The tiny white hole was clearly observed by the author in a previous Mills-type experiment of electrolysis with light water and nickel electrode. There are a lot of conic products were observed, and evolved products resulted in the tiny white holes. So basically, he saw triangles. Well, I call them triangles, but they're actually cones. Okay, so he saw them too. He published it in 1996. So, what do you think was happening? Popcorn? Rossi predicted a boson over at startup? Maybe, yeah? Kind of like coherent matter principles? No idea, John. Well, someone's honest. What have I missed from each of my recounting here? Well, I'll let you know. As I've been reading this, I've been particularly crafty in not saying something. So let's go to this. This is the paper here. Right. So I phone Alan last night and I say, Alan, I think you've already got what we need. And I explained where I'm coming from. So what I'm saying here is, I suggest using either Hutchinsonite, which is funny. It's Hutchinsonite. It has thallium, lead, 2 arsenic, and sulfur, but I wouldn't use that. I would use laurendite, and this comes from Macedonia. And laurendite is thallium, arsenic, and sulfur in one thing. And I'll show you what I'm going to suggest doing. But I'm going to go back to the cookbook is in the Signal and this paper, because there's something I deliberately overlooked when I was reading through this, and whether it's in here, I don't know. Okay, so the Geiger is talking about the Geiger Muller tube. Okay, well, it will be in there somewhere. It's certainly in here. What am I missing? I'm missing this. We used a sodium iodide scintillator that was thallium doped. What did Celani use in 2014? He used a sodium iodide thallium doped twice. He had 2 of them, and they both gave the same signal. And what did Matsumoto use? Let's go up to the start of his presentation. He used, does it say it here? I need to go down to the bit. Here you go, you can see it here. He used a cesium iodide thallium doped. Can you believe it? Can you believe it? The signal that he's seeing, I don't necessarily think is in the electronics, although we do know our power monitor in GS 5.2 went down. But could it be that this signal that was observed repeatedly by Matsumoto, leading up to publishing this in 1996. And in fact, he talked about the same thing in his presentation in 1995. And could it be that this signal here, this amazing trace that we got on trace 7 and then trace 8, could it be that what's going on is you have in the reactor the coherent matter forming, and either at the forming there is some that doesn't quite make the grade and gets kicked out, or there is an explosion and an instability. And we know from our observations of echo fuel, and we know from the star traces of Matsumoto, that you get these toroidal products coming out, which are one of the classes of exotic vacuum objects, and they are ejected. And we know from the work of Zatelepin and Baronoff that strange radiation floods their lab. We know from Hudson using Ormus and tungsten disappearing that it flooded his lab. And we know that in 2000 and when it was 2011, the 14th of January, that 7 to 8 meters away, 2 detectors detected something shortly before Rossi came out and said that the reaction has started. Something was flooding in all of these different cases. And in our case, and in multiple times with Takaaki Matsumoto, they observed this Bremsstrahlung-like radiation. I am going to hypothesize today that what is occurring is potentially an EVO is getting into the scintillator. We know 100% from the 2011 to 2012 paper by Brian Scanlan and Edmund Storms of Kiva Energy that it can go through glass, some sort of ceramic, it can go through aluminium, it can go through stainless steel, and it can get to a Geiger counter. It can go through plastic as well, right? We know from Shishkin, it can come through his iron of his cavitator. We know it can come through PVC from the work of Leclerc and interact with our material. So I'm saying that when you are looking at this experimental layout here, if we go to the experimental layout, inside this reactor here, GS 5.2, inside there, something occurred. It's either in the formation or an instability and it blew up. But the interesting thing is it happened when we went over 1000 degrees. This is, for the first time, this is the temperature at which Alexander Parkhomov says is able to start technologically producing cold neutrinos. And something came out here. It went through the Cantal wire that contains chrome, aluminium, and iron. Okay? And it didn't produce any of the characteristic X-rays for chrome, aluminium, and iron. It went all the way down here, interacting most likely with the lead, but it didn't produce any of the characteristic X-rays for lead. It went through the aluminium casing of the scintillator, but it didn't produce any of the characteristic X-rays for aluminium. And in the scintillator, for some reason, we get this spectrum that comes out with this smooth curve, which is way, way bigger than the background. So I am saying that the thallium in our detector, in the two detectors of Francesco Celani in 2011, and in the 1990s work repeated by Takaaki Matsumoto, these massive bursts were because of strange radiation, and they interacted with thallium, which has been known since before 1985 by the worldwide scientific community and agreed upon. We don't have to argue this. There's no debate necessary. That it goes from thallium-205 to lead-205, and lead-205 has a 15 to 17 million year half-life, and it needs electron capture, which is not so easy to do when you're trying to take all the electrons away from it. Okay, so I said to Alan last night, I said, you know, we don't need to buy some nasty thallium isotope, because we were coming up with a something like this, where you had this lorandite down here, a little mesh, and then up here you had your standard sort of Geiger Muller tube, like pancake tube, and you had this in a kind of steel D-wire with a kind of vacuum, okay? And this would provide a high resolution, potentially, strange radiation detector, because we're using known physics since before 1985, agreed upon. And if you get the signal, when you go over a certain temperature, you know that the beta particles are almost certainly coming from there, because they shouldn't be coming from the reactor. There's no reason for them to come from the reactor. And we already know that Brian Scanlan and Edmund Storms points us in this direction of this happening. Moreover, when you finished your experiment, you can take the thallium out of here and look for lead 205. And I said to Alan, hold on, you don't. The difficulty is, can we ever repeat GS 5.2? And I thought, hold on a minute. Hold on a minute. You don't have to redo the experiment. You already potentially have the proof in your scintillator. In that 2.5 inch thallium doped scintillator from 2016 that showed this signal that you see on the screen, we could smash that up and send that for ICP-MS. And if we see lead 205 in there, one freaking atom of lead 205 in there, it's 100% proof, 100% proof that something caused that to happen. And the scientific community would tell you what caused that to happen is neutrinos, right? It's the thing that does it. Okay? And what that would cause is the emission of beta particles. And they would cause, guess what? Bremsstrahlung radiation in the scintillator. This explains all of the observations from multiple parties, repeated at the same time with Celani, repeated multiple times over many years with Tadahiki Matsumoto, and also our observation in 2016 with GS 5.2. And it will be 100% proof that Lena can do this. It will be 100% proof that Parkhomov is right, that you can technologically produce cold neutrinos. It will be 100% proof that Shishkin is right, that strange radiation, at least in part, contains cold, condensed form of cold neutrinos. And it will at least support the notion that Matsumoto's itonic clusters do include neutrinos in the atomic mesh. So, ta-da! It's thallium. And so we don't even have to run an experiment. So we need to compensate Alan for his actual scintillator. It's not the actual spectrum analyzer, but the scintillator, the new scintillator, would cost $1,200. But other than that, we already have the experiment. And it's like, you can't fake it. You cannot fake what I'm telling you, because you can't go anywhere and buy lead 205. It just doesn't exist in nature in any meaningful way. You would have to have a neutrino gun to be able to create it, to fake this. It's not something you can go and buy. Okay? And it's going to be there. We could delay doing the test for, I don't know, 14.9 million years, and it would still have half the number of atoms in there. Okay? So there we go. So I'm going to ask your questions, but every single piece of data that I've told you about, Zatalepin and Baranov, Hudson and Ormers, Thermocore, the comment by the Bremsstrahlung, a French nuclear scientist, the EMP of fluidized electrons by Shoulders, and the fact that three different sodium iodide thallium doped detectors apparently saw this, and a cesium iodide, a thallium doped detector, saw it multiple times. It's the force with this one is strong. It's strong. Okay, so Rossi. Well, David, yes, he was next to the reactor, but the flux. Rossi's had cancer a couple of times, so go figure. We showed in 2013, October 2013, in what we called Gamma, that this occurs when, in my view, the coherent matter is either being set up or disrupted. Okay, and we repeatedly did that. In the case of the spark discharge, and this is why I'm very concerned for experimenters using the type of reactor that we're talking about with Vega, and for David and Henk, we need to up the game on the safety. Seriously, too many people have died, and that Evo blaster, and we know pretty much what accelerates that type of events. You are seeing these EMPs events, and they are as described by Ken Shoulders in his fluidized electron EMP paper. But if Rossi was just there, he would just get one flash. Now the flash, in the case of the disappearing tungsten in Hudson's work, that was enough to cause massive disruption on borosilicate glass jars in and around the lab. So you can see it's affecting solid material. There appear to be if you look at the work of so I'm referring to Gardy Pierre's question. Several authors refer to self-compression. So there's a paper, I think in 2003, I think it might be earlier than that, by Vladimir Vysotsky and SV Adamenko, which I've discussed on MFMP's channel, where they talk about the self-compression of this macro cluster. Matsumoto talks about it. I believe, and I have witnessed it in the Echo fuel, and I talked about it before I knew about Matsumoto. And so, yes, you can get these events where you get enough of them together and it self-compresses and you have like a nova. And so he talks about black and white holes, and it's interesting the way he's describing it in his book. This leads to nuclear regeneration. So you can literally put any atoms in, and you can get a selection of atoms out, but they tend to come out in the range of atoms that are suitable for supporting life. Celani didn't get upset. It was Rossi got upset because obviously if he was looking, this is Gert, I'm answering Gert Vanderler's question. If Celani had it in energy spectrum mode rather than just count rate detection mode, he could see characteristic X-rays, and then he could determine what elements that he was using in the reactor. The irony is he wouldn't have been able to do, because he'd just have seen this continuous spectra that we're looking at on the screen here in the case of our GS 5.2, and here in the case of Takaaki Matsumoto in his experiments. And I do think there is a component of two things. There's something induced maybe in the electronics, but I really, because there's so many people saying that there's neutrinos involved, and because specifically Parkinson was saying cold neutrinos can be synthesized, and at the temperature that he said it, we'd already shown that over 1,000 degrees we had our event. Okay, we'd maybe got to this threshold level where something occurs. It's like the straw that breaks the camel's back. You can have all the straws in the world on there that the camel can support, but you put just an extra one on and you move into a different regime. It's like a phase change. Okay, it's a phase change where you are not producing coherent matter, you're not producing strange radiation, and then suddenly you are. And he's arguing that this produces coherent neutrinos. And if Matsumoto is saying that the micro ball lightning, these itonic clusters needs neutrinos in there to have the mesh, then you must be synthesizing the neutrinos or harvesting them from somewhere. Well, good luck with getting relativistic neutrinos interacting. In my opinion, that's just not going to happen. But if they're synthesized, and Parkhomov says this is because you've got ions or electrons colliding in a dense situation, you get 1,000 degrees plus, you get over the energy threshold required to synthesize the cold neutrinos. And in fact, there is cosmological papers, even recent ones, that say out in the cosmos, neutrinos are synthesized when you get hot plasma together. So I think you can go and investigate that. I can't recall the paper, but I recall reading something recently. So yeah, so Rossi got upset because he thought that he would find out what is in his reactor, but actually the reality is he wouldn't. He'd have just seen this weird smooth decay that we observed and that Matsumoto repeatedly observed. Axel, as I said in my presentation regarding the 225-day reactor of Alexander Parkhomov, once you've created the active agents, they can reside in metal, as Shoulders said, and you just need to feed them electrons and matter, and they'll go about their merry way, as you've observed in the Lion reactor. They just go around chewing up carbon and making it into other elements, and so there may or may not be a net gain there. It doesn't matter if the nickel is melted once you've got... And I will specifically talk about how the dendritic structures in the carbonyl nickel lead to the production of the active agents and why and how the initial coherence occurs. I'll talk about that. I kind of intimated it a little bit in my Q&A in ICCF 22, but that's another subject, and it's a lot too much to get into now. I'm already past curfew, so I need to go soon. There may be strange radiation in obsidian. Of course, it's something that's created by a meteorite coming in, and it's a very high energy event. So lots of stress going on, and so it's possible. Am I thinking of obsidian? I don't know. Maybe I've got that wrong. I think obsidian is this like really hard glass. They might already have a working fusion reactor, but we, the people, don't. And I'm concerned about the risks. And there are players out there that are moving towards commerciality, and they have shown no evidence of knowing how to even look for this type of radiation. So it doesn't inspire me with confidence. Now, I believe we can deal with it, even if we have to bury the reactors underground, at sufficient distance. We have grown up with strange radiation all of our evolution. In every lightning strike, there will be bucket loads of it. But it's about accumulation of quanta to a point that breaks the camel's back. There is an amount of radiation that you can safely be exposed to every day of the week, which doesn't cause DNA decay. But you go over a certain level, then you destroy cells. So we know there can be, under certain circumstances, incredible fluxes. And it would appear that in 2013, we demonstrated how you could repeatedly create these fluxes. Okay, there might be technological uses for that. Okay, and this is one that I suggest around Fukushima. Around Fukushima, there is something like 1.2, 1.3 million tons of tritium-laced water. Why? Because they can use things like zeolites and other processes to extract strontium-90, cesium-137 and these kind of things from the water. But they end up with this water that you can't get the tritium out of. Okay? And they are suggesting that they will dump this into the Pacific Ocean after the Tokyo Olympics. Now, what if Zatalepin and Baranov, Hudson and Thermocore and Rossi and us are all correct in two different types of experiments in our case, and multiple experiments using different metals in the case of Takaaki Matsumoto? What if you took a DWAR, a big DWAR, and you had prepared nickel heated up, and you injected hydrogen into there, and you produced an intense flash of cold neutrino condensates into one of those drums, right? Could you instantaneously or very quickly, by cycling it a few times like we did with the Celani wire, could you remediate that tritium in situ? Now, there is a question, how many tritium ions are there in there? If they go to helium-3, will that produce a large amount of off-gassing? Will that cause an explosion? You could do these controls. But what I'm saying is, if we see lead 205 in that thallium-doped scintillator from 2016, if we see lead 205 in there, and we trace that back to all of these cases of this emission of this radiation on the initial loading or going through a transition temperatures, these key temperatures that were identified as 200 to 350 or 250 to 350, in my view, as I've argued before, it's 179 degrees to 350 in the case of nickel. If you can produce a flash of cold neutrinos and instantaneously deactivate or massively lower the activity of that tritium, why would you not want to do it? Why would you not want to do it rather than dumping that toxic stuff into the Pacific? Hudson said that he did it twice. He replicated it, and because the plastic around the wires in the lab and the glass beakers were falling apart, he decided it was probably a bad idea. So he never did it again. Look on our channel for anything. In fact, I can show you Matsumoto. I can just, there we go. Matsumoto, that's how you spell Matsumoto. Mill says that self-sustained mode does not happen until 1300 degrees C. Well, that's very likely because that's the temperature at which you really start producing cold neutrinos. Obviously, the weak force is involved because you have a beta particle being released from the thallium, and neutrino is part of the relationship in the weak force. So definitely the weak force is involved. If all the electrons are stripped off an EVO, you get all of the particles that are contained within the EVO flying out. I'm going to talk about that on my blog. I've got the first two parts of what goes up must come down. There's another two parts to author, and I will take that to the bitter end, and it's going to be unbelievably insightful, really. Just, but people should go and study EVO Blaster in the context of what I've said today, and the second one where we showed that there were radio pops incident with the detonations. No, neutrinos are basically a packet of energy wrapped up in itself. But if you look at the presentation from Andras Kovacs that we published on the Martin Fleischmann Memorial video channel, YouTube channel last night, he's arguing that the neutrino is in fact a scalar wave in the same kind of fashion that the photon is an electromagnetic wave. How that condenses, I'm not so clear on. You missed the good stuff, yes, Mark, but the beauty of this platform is you can rewind and look at it again. The cold neutrinos, or the exotic vacuum objects, they are always magnetic. So if you are capturing them or controlling them, Pneumatech prototypes, you will be able to influence the reaction. Yeah, I mean, neutrinos, if you look at Parkhomov's book, he talks about the fact that normal neutrinos are basically so small and so fast they never interact with anything, but they're about as it's like the difference between gamma ray and sort of IR, or radio frequencies rather. They're completely different in what they can do to matter or their interactions with matter. And in the case of cold neutrinos that he was studying, he had proved through diffraction gratings that they were of the order of microns to millimeters, and at this scale you can reflect them with dense matter. And also that one particular neutrino is in solid matter or dense plasma is interacting with trillions of atoms at the same time. So whilst the probability of a weak interaction is low, it's massively increased by the number of atoms that are spanned by the wave function of the cold neutrino. And the density of the matter involved. Now, if you couple with that with the fact that, according to Luciatner, within an EVO, the nuclei are packed at a density that is 5 orders of magnitude more dense than the sun. That is the density of a neutron star. In his case, he referred to it as a pulsar. You have 5 orders of magnitude more dense than solid matter, and then you have a type of neutrino that's able to interact with vastly normal, many orders of magnitude more atoms, nuclei at the same time. So there's a number of things that are coming to play. Yeah, you can get tritium vials, and that is actually an interesting thing. But it's probably the problem is that in why it was not used by Parkhomov is that tritium, firstly, it decays to an atom that is in the atmosphere. I mean, it's not a lot, but it's 3 helium, but it's a pain in the arse. Sorry, it's a pain to find. But the case of tritium is that it's a gas, so it's not dense. So the interaction likelihood is much lower. So he used cobalt 60. Firstly, it's got like a decay half-life of like 3 point whatever years. It's like 1/3 of that of tritium. Plus, it's much more dense. So you've got a vastly more atoms to interact with. In the case of thallium, thallium is again very dense. But the beauty of thallium is that it shouldn't decay at all, but there is this known transition, so they would look to you can go and look at the studies in terms of using thallium-205 as a neutrino detector from the sun, and it's actually used. Go and look at Wikipedia. It specifically says in Wikipedia that this mineral from Macedonia is used in neutrino detectors. Not to say that Wikipedia is correct, but this is a known science. Yes, Stuart, Tesla was a big scalar guy. What I'm proposing is unequivocal proof that Lena can do transmutation. And not only that, it can do transmutation at a distance. Okay? And that is something people need to care about. They need to care about it. Honestly, if you go and say to someone, I've got some lead 205 in this sample, they go, get away. It doesn't exist. Just go and have a look. So, you know, this is beautiful. It's known science. If it's there, it's 100% certainly something you couldn't fake. It's not contamination, okay? Go away with your contamination things. Probably, Steen. probably. And I will talk about that. Okay, so it's 21:46 here. I think I've talked about that. What needs to be said. If you have any questions, head over to remoteview.icu and drop them in there. That's my preferred place to answer them, because I'm going to build out that article with all of the references I've talked about here today. And like I say, I don't think you need to buy an expensive scintillator and spectrometer and so forth. It might even be the case that all of the thallium atoms that would have been transmuted in this way, if that is indeed what has happened in these various experiments, have gone. And that may be why in GS 5.3 we couldn't see the same effect. We did the whole experiment, we saw some thermal neutrons around 303 degrees or something, 302 degrees, but we did not see this kind of same signal. But maybe it's a one-shot wonder. And if it's a one-shot wonder, it's even better. It's much better. Because that means we can instantaneously get rid of that tritium. It means we can instantaneously get rid of cesium-137, or at least deal with a large proportion of radioactivity. It's beautiful. It might not be true. Okay, we have to be aware of that. But there's a lot of evidence that didn't have an explanation from many, many respected proper nuclear scientists. And the thallium compound from Macedonia is the one that I would recommend. That's the one that they say to use in neutrino detectors. And like I say, you would have something like an LN7317 pancake up here, got big fat Geiger tube in a vacuum, and then you would have like some sort of mesh just to hold the mineral back. But the mesh wouldn't allow the thallium to go down here. And you could make this from aluminium. You could make it from whatever, because Edmund Storms the vacuum chamber. Because Edmund Storms has already showed that you can get this radiation going through those materials. It's called remoteview.icu. Like the letter I, the letter C, the letter U. No, it wouldn't deactivate nuclear bombs, Paul, because nuclear bombs use plutonium, typically, always. So a nuclear bomb, which is what you've just said, uses plutonium. A hydrogen bomb almost always uses a plutonium trigger, like a that compresses the fusion material to get criticality. So and these decay through a different channel. It's not beta decay, and so this won't decay it. However, it can deal with the tritium inside potentially deal with the tritium inside a what do you call it? Inside a fusion bomb, like an H bomb. And interestingly, I think it's in 2001, you can go and look this up, there was a Japanese university professor or whatever, and he suggested that if they made a neutrino beam strong enough, they could fire it through the entire Earth if they knew where nuclear bombs, as in thermonuclear bombs, hydrogen bombs, where they knew they were, and they could cause those to deactivate remotely. In the case of EVOs themselves, if you could get the whole EVO in there and it was able to capture material and do the electronuclear reactions that lead to electronuclear regeneration, then you could maybe convert it into harmless carbon. But the cold neutrino string vortex soliton flux, this neutral thing, if it is as the Russians say, condensed cold neutrinos carrying whatever ions they happen to have traveled through at the same time, then this is more likely to affect the tritium in a H bomb. Well, Gardy, you can go and look at the papers, and actually, I didn't know much about this in 2012. I done a lot of work, but you don't have to start where I did, and you don't have to make all the mistakes I did. I'm kind of like giving you the highlights, and what I'm trying to do is demystify the remaining bits. Yes, this applies to cleaning up Chernobyl. Yes, the nastiest two fission products are cesium-137 and strontium-90. Why? Because strontium-90 replaces calcium in your bones, and cesium-137 is an analog of sodium and potassium, which are in your bloodstream. And both of them have half-lives of around about 30 years, which is really bad for animals that typically live 70 years, okay? Or 80 years. It's really, really bad. And so the beauty of those, not the beauty, but the thing that is good for us from the point of view of what I've been discussing here, is both of those are beta isotopes. And relative to things like potassium-40, which has 0.9 of the life of the so-called universe, which is very long, and it would appear that is readily able to be stimulated by cold fusion reactions. Something that is wanting to decay much more interacted with by these structures should probably decay a lot faster. Okay, so I think that's probably enough for me. It is 10, or coming up to 10. I really want to get out of here before 10. So thank you very much for your time. This setup that I had here today worked a little bit better. I hope it was loud enough for you. But I think we're getting close to understanding this, and if indeed this scintillator does show lead 205, well, it basically removes a whole lot of dross of theories in the field. It enables a better understanding of at least the processes that must be going on. At least in hypothetically speaking, inside the reactor, and the fact that they can act at such a large distance is all very important information, particularly from my biggest concern, which is safety of researchers, and secondly, the fact that we can use the fact that that can act at a big distance to remediate waste. I'm imagining now that being able to put these little charges into areas in Fukushima or Chernobyl and just repeated cycling, heating and loading with hydrogen, and removing all of the beta isotopes, and then you just have the gamma and alpha, and alpha doesn't go very far. Gamma's the problem that you have left, but like I say, a large proportion of all of the isotopes that come from fission reactions are beta isotopes, and the two nastiest are strontium-90 and cesium-137. Okay, so yeah, throw the questions into the blog at remoteview.icu. Sign up, tell your friends. I think we're going to have a lot of fun this year in the coming couple of years. Got some awesome experiments with when we can get to America with the Brown's gas device. It looks like when we can get to Japan, hopefully we'll be with Matsumoto, and we'll be able to share ideas, and also with Roishi Namaza, and we definitely want to fix Fukushima before they throw that stuff into the ocean. And lots of other fun stuff. I'd like to replicate, but at a distance, the tungsten into a monoatomic gold that was observed by David Hudson. But I would like to surround the tungsten arc with a huge array of different detectors. So thank you very much. There's a lot of information in there, and like I say, I will I will update the newsletter over the next couple of days with the material. I've actually still got to do the stuff from the previous newsletter. I've actually done the video editing and most of it, but when I realized this, I just thought people need to know this as soon as possible, because and I would like to see if anyone else has got an other explanation that fits all of this pattern of data spanning all the way back to the early 90s. Thanks, Blues Doctor. Great to see you in here. Thanks, Lena, for you. Yeah, this is killer. I mean, I you know what? I was speaking to Alan at just gone past 1 o'clock last night. I couldn't get to sleep till 1, and I woke up at 4:30 in the morning. I just couldn't sleep. I just thought I was trying to find a hole all day. I was trying to find a hole because everything I've been told points to this, and it's it's like we need thallium, and I'm thinking thallium just kills you when you touch it. You know, the whole valley in Macedonia is dead, right? Because it's so toxic. And then I was thinking, holy moly! I could have said something else, but everyone that observed this had thallium-doped scintillators. Ta-da! Okay, all right. I'll see you later. Bye-bye.